Still cozy, huh? Yeah. That's pretty crowded. Okay. Actually, I mentioned before that you can't sit in the aisles, right? Except this building, this particular room has been overflowed, and even with the fire marshal here, they didn't kick people out. So as long as there's like a single line, we can still get out and come to the fire. There's an exit here, by the way, so there's 3 exits. Because of the 3 exits, they let the people go to that. So we can actually go to the aisles, and that's actually the 10% over it, which is okay. That makes sense? So you can stand if you want to here. You can also sit if you can see the screen, but we won't kick you out in this room, but they will kick you out in the other room, okay? So you guys can sit, relax, so you can stay there. So that'll be nice. You're welcome, you're welcome. Okay, I got a video to show you.
So is this a lecture or a discussion?
Yeah, right? I have a video to show you. This is pointer fun. Ready, go.
Learn about. Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers. Oh, goody. Well, to get started, I guess we're going to need a couple pointers. Okay, this code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that.
Just remind me if I
Pointees
forget.
are separate. So, how do you allocate a pointee? Okay, well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great. This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y. Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Boom! Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah, we allocated the pointer y, but we never set it to point to a pointee. Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment. Is that going to be a problem like before? No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay, here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So are we going to switch places now? Oh, look, we're out of time. But just remember the 3 pointer rules. Number 1, the basic structure is that you have a pointer, and it points over to a pointee. But the pointer and pointee are separate, and the common error is to set up a pointer, but to forget to give it a pointee. Number 2, pointer dereferencing starts at the pointer and follows its arrow over to access its pointee. As we all know, this only works if there is a pointee, which kind of gets back to rule number 1. Number 3, pointer assignment takes one pointer and changes it to point to the same pointee as another pointer. So after the assignment, the 2 pointers will point to the same pointee. Sometimes that's called sharing. And that's all there is to it, really. Bye-bye now.
Pretty cool, huh? So that was put together by Nick Parlante, who is a lecturer at Stanford, a pretty good friend of mine, and he put some good resources together to
Don't do that.
Sorry?
No, just
All right.
I'm just commenting on the comments.
Okay, so this is, ladies and gentlemen, welcome to CS61C Lecture 5, C Memory Management. Woo! Beautiful. This is, when last we left our hero, I asked you what was wrong with 1. And I made the case, on the fly, that number 1 doesn't work because malloc might fail. And you didn't test to see if malloc returned to 0. What's the real reason 1 doesn't work? Is the hyphen. I forgot the reason I put this is to trick you again to see if you remembered that you can't have a minus sign in the names of variables. That's the reason it didn't work. So it was more like, oh, remember this from 2 lectures ago? Oh, yeah. That was the problem. So that was all I wanted to show you. So I didn't get to show you that last time, and I want to do that now. Okay, let's get rolling.
Quick question.
Yes?
The malloc int, would you have to do size of int if you already got?
Yes, and that also should have been size of int also. Like, I don't know. Last time I missed that one. There's like a size of int, not int. Thank you for that. There's 2 bugs in that. All right, let's see, quickly. News of the day. A UCLA English professor has written about the change she sees in students' deep attention, a state of single-minded absorption that can last for hours, to one of hyperattention, which jumps from target to target, preferring to skim the surface of lots of different things than to probe the depths of one. So, if you find yourself being distracted a million times by your phone and by other things, you are focused on this idea of hyperattention, where anything that blinks, it's like very, like, oh look, butterfly, woo, like that kind of thing. You need to get to deep learning often requires deep attention, okay? So that's an important thing. You want to bring something up?
I was just distracting them.
Oh yeah, right, see? Don't be distracted by the man behind the curtain. Okay, let's get rolling. Bloop, click this button on and rolling. Go. Okay, in review, this is the slide you saw last time. Pointers and arrays are almost the same. We haven't really told you whether they're different, except that you know that array is not a variable. That's the one big difference you saw. C knows how to increment pointers regardless of what they're pointing to. If it's an array of huge things, +1 goes to the next one. It just strides the right way. C is efficient, but you've got problems when you have array bounds not checked because it's just too fast to check those, and variables aren't initialized. Again, all about speed. Handles the way you change pointers. That was the example we did last time. Dynamically allocate space. Malloc and free is one way to do that. That's a way to call a subroutine, create some space, return it, now you can use it. You can also dynamically allocate space with a dynamic array, but you just can't return it from a subroutine because you can't use that space outside of the subroutine. And C gives you a ton of rope that you can hang yourself with. All right, data structures. This is how, we haven't talked about any abstract data types at all. This is the first one. Here's how you make an abstract data type. You make a struct. Just like when you were in Python, you could make 2 fields and you could just use it from the object from the class. This is how you make abstract data types in C. You make structure. Structure is a way of kind of taking a big ball and saying, oh, in this structure I need an int and an array and a this and this, and you just put a big ball and you wrap it in a struct. So here's a point. The simplest kind we could come up with is just 2 integers, like a x and y coordinate. Okay. This is how you would do this. You'd say struct point p, and now you can say point p. With this. The way you access this is p.x. This is just like Python, right? P dot the field, x and y are the fields in there, point p, which is fine, okay? You could also make pointers to these structures. Again, you know that it's called by value. So it often makes sense for me to pass a big structure to something to pass the pointer to it so you can modify read and write to it there. So this is how you define a pointer to a struct point. You say star p. And the way, once you have a pointer, the format changes from dot to an arrow. So almost universally, people pass pointers to structures. Very rarely do you have your hands on an actual structure. So very rarely, unless you're like in main, you don't make any subroutine calls, are you dot something. Almost always, here's a pointer to it, let's now arrow. So p arrow x or p arrow y to get the fields of that. The weird thing is, sometimes things, we haven't really talked about packing things tight. Sometimes if you have a whole set of sub-elements inside of a structure, you don't have clarity on how big that size of is. This character is a 1 byte, usually characters typically are a 1 byte field. Integers are 4 bytes typically. So is this structure 5 or is it 8? Meaning, does it word align? You haven't done this word yet. It means, does it round it to the closest word size, which is usually 4 bytes? So if it word aligns it, it's going to say, well, this is only 1 byte, but I need to use kind of 4 bytes for that space. So is it 8 or 5? It depends, actually. And it may word align that to make it 8. Often, we'll have examples of a string of where one of your fields might not actually be space. Notice, this is like an actual character and an actual integer in that struct. Normally what you have for structures are pointers to other things. That gets it a little bit more fuzzy of then, well, where's the storage? Well, it's not here. These are pointers to wherever the storage happens to be. And so it's a little bit more complicated. So this is an example of a node. We're going to try to build up a linked list of strings. So this is an example of how you might do that. And this is a great lecture as you're thinking, oh, look, the things I learned in 61B for building the data types, I can now do it here. Let's just use a simple example of a linked list. And now, oh, I get that. Now I can figure out how to build a stack or a binary tree or whatever you might need to do for yourself on a project or an exam. But let's do it, for example, for a linked list. So I've got char star value. That is just the space for a pointer. That's not the character. That's not a string itself. It's just a pointer to that character. And this is struct node star next. That's a pointer in a way to itself, to not to itself, the space, but to another node that's over here. So you can have a chaining of it. Type def is a way you can say to the system, hey, I want to define a new type. So rather than using only chars and ints and doubles and floats, you can make your own type, which is kind of cool. So type def struct node star list. And now what you have to write is just list. You just say list and it just works beautifully. So this would say I'm taking void, I'm taking no arguments. This new would return a new list, but the list doesn't have any space at all, so I'm going to say return null. So list new is just a null list. Okay? Thinking about that. So now, this is how you would say list add. This is an example, kind of piece of code that we had. All this runs. You can grab and copy and paste the stuff. It runs here. List, it returns a new list. What's a list? It's a pointer. It's not the actual space. It's a pointer to whatever the list is, right? Go make a list and returns that, which is what happened here, right? List new returns a new list. The space was made over there. I didn't make it. I'm returning the pointer to that. So list add, what does it do? It takes a list, which is a pointer to some other list, and it takes a pointer to a string. And here's the first step. You know, all this should be familiar code. They're just showing you what it does in an example piece of code. Struct node star node. This says, I'm going to make a new node, an actual node. Here I'm mallocing the size of the node, okay? And I'm now going to cast this the right way. So now I have node which points to a new node. Now I have the actual new node, where you know a node is just 2 pointers, right? A node is just 2 pointers, okay? Node, now because node's a pointer, I'm going to reference this guy. Its value, so I was given a list. Node value is, oh look, I'm going to copy in the string. You're handing me a pointer to a string somewhere else. That might have been temporary, it might have been permanent, I don't know. But I need to copy that in so that I have it myself. So I'm making room for that. String length plus 1, because if I gave you cal has 3 letters. String length is 3. But in the actual storage, you need 4 characters. C-A-L with a 0. So if I said string length, it'll say 3. I need to add 1 always to add for the 0. String copy handles the 0. That's why I need to have the 4. If you give me cal and I only have 3, I'm going to overrun it. I have to have 4 to have the 3 for the exact length plus the 1 for the 0. So now I'm copying it with string copy. And I've copied it. This is from string to the node value. This is how this works. It's like the equal sign. The guy on the left gets the data. The guy on the right has the data. The right argument for string copy has the data. That's the input string. The guy on the left gets it. So I'm copying one by one all those strings. And I fill them all up. Node next is list. What I'm doing here is I'm putting this as the new front of the list. So all the original, this is the list I had, like 5 things. This has become the front guy. So I'm saying this list that I had, node next, I'm making a new node. The next is the existing list I had. So I'm making the new front. And now I return the new front. That's how that works. Let's look at a picture. There should be a picture there. Let's do it together. Node was initially garbage. List points to this linked list, right? List points to that, which points to that. This is like, you remember how to do car-cooter recursion? This is the same thing you saw in a kind of standard linked list in 61A. We just taught 61A. I drew that picture, basically. Here's the string, ABC, which has 4 spaces, ABC, and then the 0 at the end of it. So then, first thing that happens is, I make a new node. That's what that does. That first line did this. Those 2 pointers are garbage pointers, but now I know that node points to those guys. And now I say, let me malloc some space. Again, now I've made space for 4 guys, but again, that's garbage. Those are garbage 4 characters. I now copy it over. It copies over exactly. No wasted space. I'm pretty happy, right? That's why I use string length for that. Now ABC is my copy. Now this could go away, and I'm good. I've got my own copy. Okay, you got to always watch who's got copies of things. It's really easy to have memory leakage on that. Like if somehow they thought the string was there, but no, the string is forever. You didn't free it. Now that's still around. This is still around. I got two ABCs. It's really easy to have memory leakage. Then the second guy, which is the next node next points to the original list. And guess what? This is now my new linked list, right? I add a front. That's how you always add things to linked lists. You add the front and you return the new front. That's how that works. Okay? Bloop. Then this guy goes away, and I'm done. Now node is this, and I return the node. See, I just added something to the front of the linked list. What did I do wrong here that I told you needed to do at the end of last lecture? I did something wrong here. I didn't check for something. What didn't I check for? Yeah.
We didn't free the memory.
Well, I'm not freeing memory. I don't need to free these guys. I don't know what they are. That might have been an array. I don't free string. It's somebody else's job to free string. It's not my job to free string. It's not that. What did I not do?
No check.
I didn't do a null check. This might have been a massive string. I mean, all of Shakespeare's works and about Chaucer's work all together. I may not have room. I don't know what I'm compiling. I don't know how much other space I've been storing. So the catch is this malloc may fail. When malloc fails, what does malloc return? 0 or null. You want to check for null. So I need to have a right below this if this variable node equals null, check something. Is that right? I gave an error on purpose. Equal. Oh my goodness. If node equals null, what did I just do? I said no to null. That's one of the most common errors people have ever done. Double equals. What people have often done, this is like pro tip, say if null equal node. Put the value on the left side of the equal. Doesn't matter, right? Equal, right? Which side it is. But if you always write the value on the left and the variable on the right, if you happen to say one equal, say you can't assign a value to a variable. That doesn't make any sense. So you switch it. That way, if you ever forget the double equals, it'll actually give you an error and not let you go by. That won't compile. That won't be an error. You could say if node equals null, clean C to me. Compiler's very happy. Go ahead, run it. Have some fun. Yeah, crazy. That's not going to work at all, right? So you got to say double equal or just switch the order. Yeah, questions? Tell me your name.
Jasper.
Jasper, go.
Why are we checking null for node when we're mallocing for value?
You are any malloc. There's two. By the way, Jasper, good point. There's two mallocs here, so you need two checks.
But we know the size of the structured node.
You do, but that may be the one that fails. You may be just literally full. We're going to talk about memory allocation today. Literally full, and the top malloc fail. The bottom one would fail too, but the point is you got to check every malloc. And so what I typically do, and I encourage people to do, is every malloc call, wrap it in something I call safe malloc. So every malloc is actually safe malloc, which makes a reservation, however many unsigned void star bytes you asked for, and then says, check if it's 0. If it's 0, it handles it gently. So every malloc in your code should be replaced by a safe malloc call, where safe malloc is a little teeny routine that says, make the malloc, check if it's 0. If it's not, then return it. If it is, say, whoa, I'm in, maybe pass a string in. I was called by list add. I tried to get memory. You asked for 5 bytes. I was not able to get it. Malloc returns 0. Error, like nice help out. Wouldn't that be beautiful if everybody called safe malloc rather than malloc? So do that in general to save yourself, to be able to have bulletproof code. Yes, tell me your name.
My name's Max.
Max, go.
Why do we use struct node after doing the type def?
We could have done that. We could have done that. We should have actually said list there. Yeah, that's exactly right. That's a good point. Yes, tell me your name.
Ethan,
Ethan, go.
what happens if you don't have
Oh, yeah.
enough space?
Is there a chair? There used to be a chair here. Let me see. Hold on for a second. There used to be a chair here. Oh, boy. Right, okay. Is it special? Yeah. Okay. Let me have the question again. I'm sorry. Yeah. Yeah, that's fine. Yeah, I have it. Thank you so much. What was the question again? Who asked me? Yeah, say it again. Sorry, I got distracted.
If you don't have enough memory, like if it's full, then like what can you do to the code to like even help? You have to like free other stuff?
Oh, no. Good question. Depends what you got, right? You might have stuff that you were kind of saving and caching to be faster, like a web cache. You say, you know what, I'll just throw away the other stuff and do that. That's one way you can do it. Or you can just gracefully help the programmer say, look, I failed here. Next time, don't do something. So you basically be free if you can to keep running, right? So you don't just do it, but don't just fail silently and crash. Otherwise, it'll say segfault, right? I mean, you try to access this. Will the error be here? No, this returns 0. It's fine. It returns 0 is fine. Try to do string copy and write something that you can't. I mean, that you start to have those troubles, right? So that's the issue. You just want to basically be bulletproof code in general, okay? All right. So that's just a little example of this. At the end of this is a long slide deck, I think, and at the end I have some examples with list, or maybe I didn't print it. I think I do. Yeah, let me see here. All right, take a look online. I think there's some extra slides that aren't printed on this that are more examples of the list notes. So take a look at the digital slides on that one for this one. All right, we've talked about, yes, question, go. Oh yeah, tons of, can you guys pass this back? There's a whole stack. Pass this back, thank you for that. Yeah, there we go, thank you for that. Good questions. And pass those all around. If you don't have a handout, please pass it back. Okay, thank you. All right, we haven't really talked about where things live. Let's talk about where things live in the system. You'll start to understand actually how memory works. Really, this is about revealing the hood on how memory works. In A, who cares? Python's so magical. Java's kind of magical too. But really C, you need to know where things live, which is again another reason why you shouldn't be teaching C to intro students. Okay, here we go. When you make a structured declaration, I'm just reading the slides, you don't make memory. You're just declaring it. It's just saying, I'm just declaring what this is, what this type is going to be. A variable declaration obviously does make memory allocation. Where do those live? A local variable, so these are all declarations. This makes an integer, this makes a node, this makes a list, this makes a string pointer, this makes an array of n integers. That's pretty good. You have that. So that's one place. That's one place when you have these local variables is one place. I haven't even used the name yet, where it is, that's one kind of thing. The second kind is malloc, which is different. A dynamic malloc request is a different thing, lives in a different place. I'll give you a name for where it is in a second, but that's the second place. There's a third place and a third way to reserve space, which is a global. Anything outside of main. Anything inside of main is the first case. It's a local variable. If it's in main, it's a local. Subroutine, it's a local. Malloc is a second place. Global variables live in a third whole place. It's actually kind of cool. So anything that's outside main, like this, int my global, and then main.
In heaven.
In heaven. It lives in heaven. It's a special place. Okay? It has global scope. My global can be used anywhere. That's kind of neat. You obviously want to be refraining from using that too much, but that's actually a good point. Yeah, question.
I have a question. Sorry, I didn't mean to have raised my hand.
Oh, okay, no problem. Okay, question in front. Yeah, tell me your name. Sagar, so yeah, go.
So if you have like a global variable, if you have like multiple processes like running that same code at the same time, do they both change that same global variable?
That could be an issue. That's certainly true. Yeah, anything that's global. And we're going to get to the issue of how hard it is to write concurrent programs that are running at the same time and accessing shared state. A global variable is available to all of them. So that's shared state, and you got to watch out who's controlling it, who had the last, just like a Dropbox folder or like a Google Drive. Who has it last? There's some issues. That's the same idea. Same idea. Yep. Another question. Tell me your name. Ishan, go.
So since the structure declaration does not allocate the memory, what about the code itself? Like where does the code?
That's great. That's the fourth place. Code lives in code's got to live somewhere, and code lives in the fourth place. These are three places, and code lives in the fourth place. That's great. We'll get to this. It's going to be fun, like how this all works. Like within about a month, you're like, oh my gosh, I get it now. Where all this stuff. It's really fun revealing the hood of like lifting and showing you how this stuff works. Yeah, quick.
And my another quick question.
Yes.
Is like, so since int my global can be used anywhere, does that mean I can like access to it from another file as well? Or?
You've got to be careful about this. Things called externs, where you can reference things externally from another file. You got to be careful about how things are working like that. So yeah, good question about where that's available. All right, here we go. Here's the final news. I didn't want to scoop this slide. Here's the slide where I tell you at least 3 places that data is stored. I didn't talk about the code yet, but data is stored. Number 1, static storage. All the globals I just mentioned, they live in static storage. That's where the global variables are. They're available for the whole duration of the program, always there. Okay? You don't dynamically make them. They're just there. Whatever the program says as the globals, they're there, they're reserved, done. Static storage. Static means non-dynamic, doesn't move, frozen. Okay? The stack is arguably the most interesting of these guys, where the stack is going to grow down with every subroutine call. The stack is going to grow. It's called the stack. You'll make new frames, the stack frames. Often called activation records. Every time you make a subroutine call, it makes a new stack frame. Every time you return, it takes it away. So it kind of grows and shrinks. Or like a stack of dishes, but we think of it growing down. Okay? The heap is, again, you can make the case that the heap is more interesting than the stack. The heap is this really cool dynamic space. Now, I want to apologize to anybody who's gone through 61B, which should be everybody, because the stack is the name for the space that dynamically grows. It grows like a stack. Beautiful, right? The heap, the name for the stuff that malloc controls, is not a heap. Just had to say that. Like, why, as computer scientists, would we call it a heap when there's already a data structure called a heap, and the stack is a stack, but the heap is not a heap? Okay, so the malloc area is what we should call it, but we call it a heap, all right? It's like the heap. Like a heap is like a big old uninitialized group, and just it's a heap of stuff. It's like a heap of dirt, right? That's what that means. That's the kind of not about the actual data structure heap. It's really ridiculous. Okay, here we go. Picture. This is it. I've actually revealed the, like, it's like Pulp Fiction. I opened the envelope. Ah, you saw the briefcase. Ah, light, glowing. Look, I'm showing it to you. And I will strike down with great vengeance if you don't know this. Okay, no. So a program's address space contains 4 regions. A stack, a heap, static storage, and the code. Now we know where the code lives. Isn't that kind of cool? When you run a program, if you're the only program running in your address space, you own all the 32 bits of that space. And if you haven't done anything, stack is mostly not done. You've called main, so maybe there's a little main at the top. If you haven't made any mallocs, there's no heap really. Static, any globals? That's your static space. And how big is your code? Small, big, depends. You could write a lot of code. You could just copy, you could unroll a for loop to just do with something. Imagine just copying, I equals 1. Let's see, array of 1 equals 1. Array of 2 equals 3. Imagine it's like 4 million lines of code. It just does array of n equals n. How silly that would be, right? Not a for loop, but just that. If you had a lot of silly code, code would be big. You could have a lot of big code there. Or if you had Photoshop, which is a huge code base for all the million things they do in Photoshop, that code area is actually pretty big. That factors in. Give me an example. So here's an example. Here we go. Stack has local variables. I talked about that before, and it grows downward. The heap is malloc, and it grows upward. And how clever that is to actually have the same shared, like uninitialized region be growable by both the stack and the heap. So there are some examples where you have almost no heap, like no malloc, no reservations, dynamic of memory, but the stack is really big. Give me an example of that where the stack grows really big. No mallocs, a lot of stack. Give me an example. Go. A big recursive, a big fractal. You've got 1,000 levels of Fibonacci going out of control. What happens when it goes out of control? Stack overflow. Everybody get it now? The stack has overflowed and I can't get any more. Hey! Huh? You finally get it? Wait, hold for a second. Also, you can't stop it. What I mean is, there's nothing in C where I can say, can I make another function call with the memory that I have? Malloc you can. Does malloc, hey, make a malloc call. Make my heap grow. Is it 0? Okay, I can't grow anymore. Sorry, I can't do more, a bigger Photoshop file, whatever you want to do. But the stack, you can't control. There's no way that you can query to say, could I make another function call? Can I make one more recursion level of Fibonacci or not? You can't know that. You just crash. And this is the reason why C is a language that's challenging. In most languages, you can't check that. But the point is that Stack Overflow, it can't be something you try to test. Dan said make your code bulletproof. You can't really. It'll just overflow and you can't stop it. But that's the idea. How about the opposite? Let me finish the thought. What's the opposite? Give me an example. No stack growth, huge malloc. Give me an application. Give me something that does that. Why would you ever need data? Yeah, tell me your name. Go.
Matt.
Matt, go.
Huge matrices, like we have to allocate.
Big matrices. You got some big old linear algebra thing, huge matrices. Give me another thing that you're probably using. Yeah, tell me your name.
Andrew.
Andrew, go.
Maybe like Google Drive, anything that requires upload.
That's different. That's more storage on the disk. I don't think of that as being something you need to kind of malloc unless you're locally saving it in memory. I don't think of that as much. It's a storage thing, but not so much a memory thing. It's more memory in the global sense on your disk, less about your actual memory footprint live. It's a little different. Did you see one? Give me something. Yeah, tell me your name.
We have Prashant.
Prashant, go.
Like a huge file structure, like a binary tree that keeps on growing downwards.
That's true, yeah. If you were if you like loaded a huge tree and you were doing that, if you like needed to like, if you're trying to like store the internet and like make all the links and you're making a tree of all the internet links, that could be big, I get that. I want a simpler thing that probably you've all used. Tell me your name.
A game? Oh, Dan.
Dan, go.
Game?
Oh, you gotta sit in that same place, so that's a Dan area. A game, give me a game, example of the game.
I don't know, any game.
Like what game would you do? Give me a game.
Civilization 5.
Why would Civilization 5 need a lot of memory? No, that's fine. Why would Civ 5 need so much malloc space?
Because you're handling graphics and
Right, maybe there's a lot of geometry that you need to load into the system. You load from a disk or from the web, you load it in and then you need to render it there. Here's one that no one suggested. Oh, you got Mickey's got one. Mickey's got one. Go. Do you have more?
Video editing?
Video editing. You got a large video file. You got to be doing something. How about even simpler than that? Photoshop. Any image editing file, any imaging program, you say make a new file. You can say, rather than load a file, you can say make a new one. You can just draw on, right? I want to make a new canvas, a virtual Photoshop canvas, right? You say, give me your X and your Y. Your X and your Y times what your bit depth is literally a call to malloc. I'll say it again. You say, I want to make a new window in Photoshop to be able to draw on. I want to make it 1,000 by 1,000. That's 1,000,000 pixels. Each pixel is maybe 4 bytes wide, RGB and alpha. That's 4 times, that's 4 million. You just literally asked for a malloc of 4 million bytes, plus overhead and header stuff. You get it? You make it 2 million by 2 million, that's now 16 million. You get what I'm saying? So you're literally making a call to malloc when you tell it in Photoshop to make an image some big so you can do some things. So it's I want you all to go to your Photoshops, which you all have access to thanks to the Adobe Media Cloud, Creative Cloud. Keep making it bigger and bigger and bigger. No, I'm not joking. Until at some point it will gracefully say, I can't make an image that big, either because your memory on your memory doesn't hold it here, or what it actually does is use some of your disk to actually kind of be memory. We'll see that later in the memory hierarchy. At some point, there's going to be a limit, right? There's got to be a physical limit to how big the Adobe big document is and hold it there. That's a literal call to the heap, to a malloc request that calls the heap and grows the heap. Isn't that kind of cool? Kind of neat, right? Okay. Static is global variables. Your code lives there. That's kind of cool. Now, here's the key thing. Somehow, the operating system prevents these two things from crashing. The OS is kind of watching things and making sure that you don't overlap and those things don't cross. When they cross, bad things happen. Yes, question in the back. Yeah.
What if like heap and stack, we have so many things on heap and stack. What happens like when they're about to like cross each other?
Well, if they're about to, but they haven't, you're still good. The moment they cross, you've got an error. Either malloc will fail, which you can gracefully handle, or the stack grows and you can't handle that and you'll just crash. That's the trouble. You can't catch the stack. You can't know that. Yes?
Since stack and heap use the same memory,
Yeah.
Could you use malloc to check if you can make another?
That's a good question. Can you use malloc? The answer is no, and I'll show you why in a second. Great idea. Really good idea, but you can't do it. You have a question?
Yeah, so...
Tell me your name.
Renee.
Renee, go.
Yeah, so he has space for pointers. If the pointer is pointy something like the pointy, where would the memory be? Will it be instead?
Oh, that's a good question. Like there are many questions I ask on exams. Where is the pointy? I got a pointer somewhere. You got to know where there was. Where was the original space? Was the original space an array? Which case is on like a local variable that's an array that's on a stack. Was it an array that's a malloc thing? Then it's on the heap. It's basically that. Was it a global? You can make a global array, like int AR of 20 on top above main. Then it's in static. Depends where the original space was reserved. All right. Where are they at? This is the question. So Renee was asking, where are these stuff allocated? We're going to teach you how they are. Okay, here we go. So if it's outside a procedure, global, then it's static. I said that already. That's redundant. If it's inside a procedure, it's local and on the stack. And freed when the procedure returns. I kind of talked about that. You can't use my string as to make some, hey, go make a string and as a subroutine in a local array and then return it to me. I can't use that. It's freed when it returns. You can't have that. And main is a procedure, okay? Here's why. This stack is a series of frames. Every frame is like a procedure call. You think of this, okay? Each frame contains the return address for where to go back to. You ever like make a function called fib of 10, calls fib of 8, calls fib of 7, and it goes back and eventually comes back and fib 10 works? How did it know how to come back? Because in the frame, it knows where to come back to. It's really very cool. It's a function call. It means when you come back, return back to this guy, and then you reset the system in some sense to the guy who called you. It's there. All the parameters are passed in that stack frame. Call by value, which means all the values are copied. Now we know why we pass pointers, not structs. You pass a big struct, I got to now make this much bigger. The stack has to grow because you're passing call by value on a massive struct, not the pointer to the struct. That's why we like pointers again. All local variables. The stack frame is contiguous, blocks of memory. There's no gaps here. Folks, this stack is contiguous. All those frames solid, no gaps. There might be gaps in here. We'll talk about that in a second, okay? No gaps. When it ends, the frame is tossed off. I have a little animation for you. It's a little PowerPoint animation. Here we go. A calls B, main calls A calls B calls C calls D does nothing. Watch what happens. Main loads up. That's what happens when main is running. Oh, there's a function call. A. So the stack pointer is the bottom. The stack pointer is the guy that keeps track of the lowest level of the stack. It's like the bottom of the stack, right? Because it's a contiguous, right? So what's the pointer? It's the pointer to the bottom. So now I call A. Well, I got to do what? I got to copy all the values over. I got to copy the return address over. And whatever local variables A has, which are none. But I had there's a little frame that I had to make for A. And now watch, bloop. Now the stack pointer went down as a result of being in A. Now I'm in A. A can now get back to main because there was a return address for what main was. I know the line, literally the line after the call to A. Like, how does it know? You ever like trace on your finger like where code goes, and you go to here, and after calling back, what's going to happen next? The program right after A. Well, somebody's got to remember it's right after A is where you're going to come back to. That's what's stored in the return address. Go right back to the guy right after A. See, that's how it keeps track. You ever wonder that? The magic of how does it know where to come back to on a recursive call? Anybody ever wonder that? Nobody ever wondered that. I used to wonder that. Now you know. If you didn't wonder, you should have wondered. Now you know. Right? Because this return address keeps track of it. When you make a new stack frame, you got to remember where to come back to. That's who kept track of it all along. This is why 61C is so cool. Like, keep lifting the hood on things you like should have wondered about all along. All right. A calls B. I got to make a copy of whatever the value of this 1. That value of 1 better be copied over. The local variable N is stored here. Here's the return address. What's the return address to? The line right after B. So now I know how to get back to the guy, to the B, to the right after B line. That's stored here. Plus whatever the local variable of N, whatever that value 1 is, that 1 is stored here, and N is set to that. I make a call down to here. Now I got to move it down. Now I call C. That's the yellow, that's the green guy. The colors kind of went off. There should be all the colors of the code, but now that's C. Now I know how to get back to B. I got to copy the O. I got to copy the N over. So the local variable O is set to that. Stack pointer is the end of C. Now I call D. Okay? D has to be able to get back to C. So this is how to get back to C. This is how to get back to B. Right? This all works back. Okay? D finishes. This is the beauty of PowerPoint animation. Watch this. D finishes. It just goes back. D returned. Now it's right below the call to D. It's where we're still running. That's where my finger is. Does C clear this? 1, 2, 3. No time to clear it. Whatever data was here is still there. Okay, let's go back. Then D returns. This line here. This returns. Now I'm here. Now C returns. Bloop. Now that just goes up. The stack pointer just goes back where it was before. Okay, it comes back. B returns. A returns, and now I'm back in main doing what I got to do. More stuff to do? No, I'm all done. I flush the whole thing and I'm done. Question. Tell me your name again.
Andrew.
Andrew, good question.
So is C tail recursion optimized?
Is C TCO? C, that's a good question. That's a very good question. I have to think about it. I have to think about it. Depends. Boy. Because the compiler could do a lot of work to actually TCO it. I will look into that and get back on that. I don't know. Good question. Thank you for that. Yes. Ted TA, go look into that. Thank you. Go.
So you were saying that there's no time to free that memory in the stack, but then where does it get thrown back into the memory that's available?
Well, here's what's beautiful about this. And when I give it back to the world to be used, the moment it goes up, now if the heap needs it right now, bloop, the heap can come up and take it if it wants to.
Oh, so if there's some stuff there, then that's the garbage that comes from.
Yeah, that malloc will just, if a big malloc goes roop right now, guess what malloc can do? If you just probe this memory that's yours because malloc gave it to you, you can just start looking in all the data that was there before. All the data. Raw passwords and ASCII, thank you very much. It's mine. Thank you very much. Seriously. You can just read and write. All the stuff is here. Once you malloc it and it gives you this area, it's all yours to read and write. It's kind of fun, actually, to do that. In fact, I encourage you, if you want to make a stack that has a local character array of like just words, like just Shakespeare words. Just fill it up with Shakespeare words, a dynamic local variable. Then clear it, and then get a big malloc and see if you can read what's in there. You'll read the words. It's beautiful. It's really interesting. Yes, question?
So in that case, malloc or like heap or whatever would be able to know where the stack pointer ends, right?
How does it do that? The question is, how does malloc know where the stack pointer ends?
Yeah, and can we access that?
Well, because the catch is you don't know. Malloc is not contiguous either. So malloc is all fragmenty. I'll show about in a second. So you can't really know by making mallocs where it'll actually be. You could actually ask, malloc returns the pointer. So you can actually print out where I get it. You can make a big chart and show you like visually where those things are. So malloc will tell you what the address is and it'll show you what it is. You want that one that's up here. Because you could say, hey, look, I make a variable A. Okay, I make a big character array here, like Shakespeare's works, right? And I say, what's your address? Now I know where it is. Now I can malloc it. Where are you? Oh, you're down here. I keep getting to malloc until I get in that region. You'll start seeing that data. Quick question. Yes?
Does that mean even we free the memory, the data is not cleared?
Correct. I said that before. When you free memory, it's not cleared. Free memory is just return the point. Okay, we're gonna keep going. Keep going. I got this. It's like 4 more slides, and I gotta get through this. Thank you for that. Come back. Come to the end or ask questions on the live Piazza chat, which we have live. Thank you very much. Awesome. Okay. Phew, this is a great slide and blows people's minds because they don't realize what happens. Look at this example. Watch what happens. Here's main. Let's go slowly. Make sure everybody gets this. Here's a pointer to an integer. It's called stack address. Here's some content, okay? I call pointer. What does pointer do? Look, makes a local y, sets it to 3, returns the address of y. Ooh, already I see a problem. It's returning the address of local storage. You're not supposed to do that ever. Let's see what happens. Watch what happens. Then I return the pointer to where y is, okay? I say stack address is that pointer. So now I have a pointer to that where the y was. You got that? That's what this line does. Then I say, go grab that. Go to that stack and grab the y. Okay, content y, okay? Print it out. It prints 3. Look, here's main. Main calls pointer, makes a y down here. Stack comes back up, I'm in here. It says, from main, point down in here, grab the 3. Get the addresser here and grab it. It grabbed it. Print it out. 3. Go grab it again. Print it out. Garbage. What just happened? I got excited. What just happened was
That's pretty exciting. It's pretty exciting.
Print is a function call. So print was a function call. It had to grow the stack for print. There's all this internal stuff for print. I don't know how print works. Abstraction, I don't care. But print probably wrote around all of its storage it had. It overwrote the y. So when you ask for the y again, when you literally say, go follow that same pointer to the illegal area you weren't supposed to be accessing. It's like having a key to your old apartment. Anybody have the key to the old apartment? You're not supposed to have that, okay? That's the key to the old apartment. You go in once, oh, that's my stuff is still there. Then you go away for a year, people move in, you go in again, that's not my stuff! That's your garbage. Oh, look, it's garbage! Where my stuff is now the garbage can, okay? Isn't this cool? This is a source of error. People blow, like they say, oh, this is what makes people believe. This is why if you're learning it in CS1, your first course for majors, you think computers are magic and non-predictable because you get this kind of behavior in C. Again, reason number 4055 why we don't teach C to intro programmers. The heap. We talked about it as this dynamic pool of memory you can grab stuff from, okay? Back-to-back requests for malloc could be really far apart. There's nothing about it's only contiguous within one request. If I say malloc of 100, I guarantee 100 contiguous spots. But malloc of 100, malloc of 100 twice, it could be over here. Who knows where the next open space is? So, in C, you gotta specify the number of bytes. I told you about that. We talked about uninitialized space. That's all new. Memory management. How do you manage memory? Well, code and static don't move. Static means static. Code is inside the code. I haven't talked about that really. The stack space is easy. The stack space is a FIFO. Literally a stack just grows and grows and grows, and you move the stack pointer to move it up or move it down to make more space. That's really easy and fast. Memory management in the malloc is really complicated and slow. Why? Well, you want them to run quickly. Okay, but there's a thing called fragmentation. You ever heard of disk fragmentation or disk defragmenters, where things like get all slivery? That's actually what happens to malloc. If you start running a program and just having normal memory exercising, read malloc free, malloc free, malloc free, there'll be all these slivers in the heap, all sliveried up. That if you could somehow coalesce them, it'd be great, but they're not. They're all slivered up, and I'll show you exactly. This is called fragmentation, okay? So, here's an example. I want a malloc 100. Bloop, there's your 100. I want a malloc 1. Bloop, there's your 1. I want a malloc, oh, let me just free the 100. Bloop. Ladies and gentlemen, we just got a fragmentation situation. And if this is my whole memory, like 150, if I say I want like 140, well, I have 140. There's like 100 here and like 40 here. But I can't give it to you. If this is my whole memory, I cannot give you 140 contiguous thing. I will say 0. What's your address for your 140? Sorry, null. I return null. I couldn't give it to you because I don't have 140 contiguous spots. So this fragmentation is a real issue as you start to have memory that's exercising your system. You have all these slivers, and now you want a big thing and it fails. You actually have the space, but not together. And malloc's deal is I have to give it to you together so you can just stream an array and do that thing. I can't give it to you. Sorry, I've slivered it up. See how that issue? And so the question is, now I ask for 50, where do you put it? That's the interesting part of the design of the malloc system. Do you put it on the top? Do you put it there? Do you kind of pack it in tight? Where do you put it? That's the fun question. So let's talk about where you might put it. There's a thing called the free list, that all the free blocks are this circular linked list. Imagine a linked list, but the end points to the front again. It's like a circular linked list. It just goes around. Okay? So here, there'd be 2, 1 and 2. 1 points to 2, 2 points back to 1, right? It's a little circular thing of all the free blocks I have, total. Initially, it's 1, big one, and then it breaks up, okay? When you're doing it, you search for it along the circular list. Well, how do you search a circular linked list? There's many ways to do it. It's malloc. Here's the Cardigan-Ritchie implementation. You search the free list for the block that's free enough. You just keep going. Are you free enough? Nope. Are you free enough? Nope. Are you free enough? Nope. I just walk the whole list. Oh, you free enough? Yes, great. I'll grab it from you. Okay, that's one technique. Okay? Free does this. Free checks to see if I were to free R2, what should it do? If I free R2 right now, what happens? It has to collapse the neighboring guys into, like, it both gives me back this 1 and also collapses them one into one bigger one, right? So obviously free's going to do that. Free's going to obviously coalesce 2 neighboring guys, or free a middle guy, right? That's great. Yay, free! Frees it up. Now I got a bigger spot in the middle. Okay? So there are 3 ways to do it. Best fit, first fit, and next fit. What's best fit do? Best fit says literally go through everybody. You know how long your free list could be? Really big. Do you understand that? I make a call to malloc. I expect it to return like in 1 cycle, 2 clock cycles. No. It's literally internally walking a linked list that could be hundreds, thousands, millions of sliver elements long to find the guy that perfectly fits. When it finds one that perfectly fits, like let's say it'll stop early. If I want 100, I found exactly 100, I'll just stop now. I don't have to keep going for that. Once I found one that fits. But if they're not perfectly fitting, I'll keep looking for the one that fits exactly right. Think how slow that could be. That's crazy. Malloc could be potentially really slow after your program has been running for a while. What programs run for a while? I don't know, web servers that run continuously for years. If you don't handle memory well, you could really be in trouble. First fit says, look, I got the beginning of my circular linked list. The first guy that I have spots, I'll stop. Do you have room for me? No. Do you have room for me? Yes. Okay, good. First one. I was hungry. It's like the first place you go to a market when you're hungry. Thank you. I don't even care if it's like a liquor store. I will go in to get a burrito or something, right? Even if it's nasty, I was hungry, right? That's first fit. Next fit says, you know what? What happens by first fit is you're kind of always hitting the beginning, always making these like slivers and pebbles at the beginning. So next fit says, maybe I should just remember the last where I was and then start from there the next time. Does that make sense? So I remember here, okay, next time, a new malloc? Okay, I'll start from you now. Okay, got space here. Next time, it'll be starting from you. I got next fit remembers where you were. Just one state variable telling you where you were last. That makes sense? So best fit, search all of them until you find one that exactly fits best. First fit, always from the beginning. First one you get that works. Next is just keep rotating it around in a circular linked list. Yes, quick question.
Can you free space and next fit adjust?
Yeah, free phase always coalesces. It doesn't really use it. So just free will like look at the neighbors, look over here, and do this little thing. Yeah. Okay? All right, here we go. Yell key wife. I don't know. I didn't make the name up. Yell key wife. Here we go. Okay, see that works. And I think I have my thing here. Here we go. The con of first fit is it results in many small blocks at the beginning of the free list. B, the con of next fit is that it's slower than first fit since it takes much longer in steady state to find a match. The con of best fit is that it leaves a lot of tiny blocks. Okay, here we go. Con means like downside. What's the downside? What's the disadvantage of each of these guys? First fit results in many small blocks at the beginning. Next fit is slower than first because it takes longer at steady state to find a match. And best fit leaves a lot of tiny blocks. Does it work? Does the wife thing work? The yoki? Yes, thumbs up. Thank you for that. Sorry. Okay. All right. Keep looking. Keep voting. Think about it. I have like a little bit of time. You got that? Okay. And talk to your neighbors. Go. Discuss. Meanwhile, I'm going to look at this. So ignore what I'm going to say here. I'm going to look at this. Oh.
One, the quest stuff has been posted, and then two, if they have conflicts, they need to make sure they fill out the form today.
Okay, I'm gonna give the mic to you to say those things. You gotta go. Yeah, I do too. I'm sorry. Okay. Okay, and result. Vote for result, quick. Let's see if you can vote. I only got 13 votes in the last time, so I hope there's more than 13 people in this room. There's 13 people sitting in the back, actually, so let's try to get that one. Okay, vote. We got 1 minute left. Let's see if we can do this. This is gonna work. I made it to the finish line. I actually finished the lecture. Okay, here we go. Okay, you're voting. Stop voting. 1, 2, 3, stop voting. Here we go. What'd you do? 20 for the first vote. And cancel this. And how many got here for the second vote? 38 for the second one. What'd you say? Mostly, what are you saying? Mostly you're going TFF. That's what I'm getting. Most people TFF and TFT. So TF and then you're not sure what the last one. That's what I'm getting. Okay. Oh, I thought I had the actual answer here. Let me see. I go here. And there's go to. Used to be there's a go to. There's a hidden slide. Where's my hidden slide?
It said hidden.
Oh, I took it away. Okay, let's do the first one. Here we go. So first fit. Do you get many small blocks in the middle of the free list? Beginning? True. The reason first fit keeps like hitting the front, making all these slivers at the front. True. How about next fit slower than first fit? Slower? False, right? That's the benefit. By going next, you don't have to keep hitting the pebbles at the beginning. Like kind of like the ocean, there's pebbles and the big rocks in there. Stop hitting the pebbles. So go to the bigger rocks, we have bigger stuff there. How about best fit? Lots of tiny blocks? Actually true. If you keep doing that, you often get these slivery guys where it's like, oh, you have 101, but I wanted 100. Sliver. Boom, there's a sliver of 1. And all that eventually adds up. Okay, so that's an issue. So now it's longer. Now your best fit, if you're looking through a longer list of these small slivers, it's a little annoying. But you're packing it in as tight as you can, but you get these slivers. It's like there's no right, perfect answer. I can give you a particular workload to make each one of these look really bad. This is important. Each one of these can be made to look really good or really bad depending on the workload I give you. There's not really a singular answer, which is why we're talking about it. Okay, in summary, 3 pools of memory: static for globals, stack for local variables, heap for malloc guys. Here are 3 techniques: first, next, and best for trying to look at that free list in malloc. Okay, we'll see you guys on Wednesday in the normal room. Thanks so much, everybody. Woo. Oh, 2 announcements really fast. Thank you.
If you have a conflict with an exam, make sure you fill out the form that we have on Piazza. And also, we've released the quest information.
Okay, so quest information is out. We have an exam exactly in a week in the evening. Don't forget about that. Read about that. And if you have a conflict because you can't make it, tell us today. We got to know today to make rooms for you. Thank you so much. Okay.
Shouldn't this be struct point or like?
Yes, yeah, that's a bug. That's a bug. No, I actually noticed that before, and I never fixed that. Thank you for that. Thank you. That's perfect.